Let's look at another property of DTFT called conjugation. If I take the conjugation of my time domain sequence, how does the Fourier transform, the discrete time Fourier transform look like? Okay, so let's consider the normal way. You're computing your Fourier DTFT, and xn becomes like x star n. Now, it's very simple. So, basic idea is you have to convert it into a form which resembles x e to the power j omega, which means that you have to make your xn convert this into some form of xn. How will you do it? So, if you take the conjugation out, something like this. So you have your xn and the star goes out. So then this minus sign also goes away. And now you know how to represent this in terms of x e to the power j omega, which will be basically this term has to be replaced with minus of omega, and this becomes x e to the power minus j omega whole conjugate. That's what we had to prove. Next, another property from Parseval's theorem. So what is the, okay, we'll look at the implication of Parseval's theorem in a while in the next slide. But let's see what the property says. So the property is that x1 into x star of 2, this summed over all n is equal to this form. Now how do you prove this? If you try to see the form of this, the proof may look easy. So what is this? This looks like convolution. So let's use convolution. So what is convolution? The basic form of convolution is x1n, x2m minus n into x1 into so summed over all the n. So which means this is x1 convolved with x2 at m. But here there is no m. So if I take my m to be equal to 0, then I'm perfectly alright. So basically this is the convolution of two things. Okay, this negative sign will take care of it later. This is convolution of two things computed at m equal to 0. So what is this? This is basically in this form. Now if I take the Fourier transform, TTFT of convolution, it is product of the spectra, right? This is simply the product. Now I can use the form of IDTFT to write the complete expression. So this thing, x1 convolved with x2 at 0, this is the IDTFT of x1 into x2 computed at n equal to 0 or m equal to 0. So this thing goes away. So this is what I obtain. So now this looks something similar to this right hand side term, but there are some things to be straightened out. There is minus n, whereas we need plus n. So let's define x3, that x3, so I want to replace my this x2, which is, yeah, it's here, this x2 of minus n with some x3 star of n, right? That's what I have written. If I do this, then immediately I know if I take the Fourier transform of this will be x2 of e to the minus j omega, because time reversal reverses the frequency scale also, and conjugation will bring conjugate as well as frequency reversal, right? So just I substitute it back here, so that's what I get. So this means that my x1 of n into x3 star of n, so consider this form, summed over minus infinity to infinity. This is equal to this part 1 upon 2 pi integration minus pi to pi x1 e to the power j omega into x3 star. So here it is x2 of e to the power j omega, and I know this minus sign can be deducted, like if you take minus omega, then so I get x3 star of e to the power j omega, e omega. That's what I had to prove in the first place. This is Parseval's theorem, right? So now there is a natural corollary of Parseval's theorem. If I take my x2 of n to be same as x1 of n, then what I get is x2 of n or x1 of n into x1 star of n, which means x1 mod square, and summed over all the n's. This is equal to, the thing here is my x2 of e to the power j omega will become same as x1 of e to the power j omega, because there was a conjugate, complex conjugate here, so you get the mod square. So what does this imply? This implies that the energy in the time domain, so this is energy by amplitude square summed over all possible n's. This is the energy in the time domain. This is same as the energy in the frequency domain. So this is the mod square of the frequency domain and integrated over all the omegas. So this is the corollary, that the energy in both the domains is same. This is how we define energy. And then we have energy density spectrum, which is defined in this way. Basically, x e to the power j omega mod square is called the energy density spectrum, because it gives you the distribution of energy, this term is energy, with respect to omega. So you have Sxx e to the power j omega, and this is the omega is here. This is the distribution of energy with respect to omega. Of course, you have to go only between minus pi to pi or from 0 to 2 pi, because it's a periodic thing. So this is how. So these were some important properties of DTFT. Thank you very much.